Okay, so as stated, this is where we begin today. So it's not that if you leave milk out for, per se, 3 hours or something to that extent. We're talking perhaps overnight, okay, to where something like that, those acids inside begin to break down. And I'd be led to believe that butanoic acid is probably in there to some content should it break down to that. And one of the reasons is because of the physical properties of acids we had just briefly discussed yesterday was, I thought it was on here yesterday. Bonding between two carbons. I think we read it in the book. The physical properties of acids that they have very low boiling points. So therefore, that's why you keep those materials in the fridge, whether it's cottage cheese, cheese itself, milk, of course eggs, although that's considered a dairy product then as well. But again, just because of the physical properties of these compounds. As I see, we got on the schedule esterification. I wasn't sure whether we would get to that today. It doesn't look like it, so we will save that for tomorrow. We'll have your next paper that we'll hand out, and we'll give you some time to work on that. We'll do that here in just a few minutes. Okay? So then it's hard to visualize what that's saying until you write that down. We'll save that for the last. We'll come back to this. Okay. Okay, so carboxyl. So this is what we had discussed yesterday. I want to get through this, and then we'll save that. That's where we'll start on Friday, because as you can see, this is where we want to get to on Friday. Okay? So this strong base, we said, it could be anything that's associated with that of a hydroxide compound, whether it's sodium hydroxide, potassium hydroxide. It's probably an alkali metal with hydroxide compounds. Has anyone, and I'm sure this happened to anybody, might leave butter out overnight, or maybe a milk product out overnight, or you can certainly tell if you're walking down this hall if someone leaves a carton of milk in their locker. Because again, over time, what's happening is because of, again, these physical properties, when we're looking at some of these acids that are in there, their melting point is just so low that they begin to break down, and that's why you got to keep them in the refrigerator. So then when you leave them out in, not you individuals, unless you did at one time, I'm sure maybe you've all been there too, left it out in there, and then your locker begins to smell because some of these, again, acids that are inside of these compounds begin to break down. And it's not formic acid in here, it's the fatty acids in the milk, okay? So it's not these specific organic acids because, again, when you're referring to organic acids, the physical properties, as you can see, are so much lower than those that are ionically bonded like what we see here. Now, from general chemistry, okay, what would be your clue here to know that this is so much higher because it's ionically bonded? How would you know that that's an ionic bond from last year or from physical science? The base definition we look at an ionic bond is that between what and what? It was a little while ago. What is sodium? What state of matter? Or not state of matter. Where's that at on the table? Sodium. Okay. So then, since it's way over there on the left, is that a metal, metalloid, or non-metal? So I heard metalloid and I heard non-metal. Someone want to throw their hat in the ring and say metal?
Metal.
Okay. Sodium is a metal. That's right. And then when we look at the formate ion, okay, this is all covalently bonded, but a metal and a non-metal is an ionic bond. These carboxylic acids are all covalently bonded because they're all non-metals, okay? And that's one of the things we'll discuss when we start making that soap again, is how it interacts with the water, because water is a polar molecule. Even though it's covalently bonded, okay, it's polar because those charges are partial positive and partial negative, and then that works with this type of a compound. As we see, a carboxylate salt is, for instance, could be sodium propanoate or something to that effect, okay? Because an carboxylic acid reacted with a strong base, sodium hydroxide. This, again, is a metal, so it becomes an ionically bonded compound or polar, and that's why you can wash dirt and grease away with a substance like the soap that we will attempt to make. So I think we had mentioned get through this one, and then the physiological conditions, and I think we would stop, we would stop there for today. So why stearic acid is not water soluble? Why not? All those bonds in there, are those electrons shared or completely transferred? In other words, what's the bonding in this acid? Is it covalent or ionic, do we think? If it's covalent, so therefore it's not water soluble. So then what is it that makes sodium stearate water soluble? Because that's an ionic bond, okay? That's right. So once you start throwing an ionic bonded compound in there, that makes it water soluble, where stearic acid then is not water soluble because the bonding is covalent. Okay, we'll get through this next slide here, and then tomorrow we'll begin with this and we'll get on to that process. Okay. So again, these physiological conditions that we see, okay, whether it's citric acid, that we can't absorb that because it's insoluble. It's once you change that to its carboxylate salt, we can absorb it, because once you do this, again, got to keep in mind, you're referring to salt. That means there's going to be an ionically bonded not molecule, but ion in there. Therefore, we can absorb them and utilize them. Now, there are examples within the human body that we do not want to be dissolved, okay? And one of them has to deal with, cholesterol, okay? What do we know? What do we remember in A&P about cholesterol? It's the base molecule for complex compounds like maybe aldosterone. I could have given you a simpler clue than that, but do we remember what aldosterone is? Does it sound familiar? Say that? It's a hormone, just like that of testosterone, estrogen, okay? Those, okay, are steroid hormones, and you have your non-steroid types like norepinephrine, epinephrine, renin was another one that we had discussed. Of course, there's a whole table that we had gone through, but those we do not want to dissolve in water. That way they can be transported through your bloodstream from point A to point B. But when it comes to something that we want to absorb, okay, it's changing these compounds, these fatty acids. We'll really spend more time on that when we get to the vitamins, because those are also different types of fatty acids. It's how the body metabolizes them, and that will be in the biochemistry section of this, okay? So all of these allow for quicker, more efficient absorption because you're changing that bonding in there. Okay, so that's all I have. We will catch up to you next time. I will collect that paper and then send this one out and send you on your merry way. Catch up to you next time.